After a detailed analysis of translation matrix, today we are going to explore the concept of a refraction matrix. In fact, this refraction matrix is also very important matrix to deal with the matrix method in geometrical optics. When you say refraction matrix, in fact, this matrix represent the effect of refraction. As you have seen, the translation matrix represents the effect of translation. Similarly, this refraction matrix, as the name says, this represents the effect of refraction. Actually, here we will see to how to find this refraction matrix when refraction takes place at a curved surface. So you can see this figure. I have considered actually a convex spherical surface, and this convex spherical surface is this dp. You can see the figure, and again this z-axis has been taken as the axis of this convex spherical surface. And let us consider there is a point A where you can imagine there is a point source of light, and from this source of light a ray of light AD is incident on this spherical surface. And again we are considering that this incident ray AD is actually a paraxial ray. When you say that AD is a paraxial ray, what does it mean? It means this AD will be very close to AP. Or you can say this angle at A, which I am just marking here by this theta will be very small. And if theta is very small, this point D will be very close to this pole P. So D and P are almost at same position, although for clarity I have shown this point D far separated from point P. But the actual situation when you consider that AD is a paraxial ray will be what? That this D will be almost at the position P. So in one sentence you can say that we are considering that our incident ray AD is a paraxial ray. And this spherical surface you can see in this figure separates actually two homogeneous media with refractive indices N1 and N2. Or you can say the refractive index of the medium in left side of this spherical surface is N1, and that in its right side the refractive index of the medium is N2. We consider it. And you can see this C, point C, which lies on this z-axis, is the center of curvature of this spherical surface. And so this PC, which will be equal to R, it is actually the radius of curvature of this spherical surface. So since C is the center of curvature, so if you will join the point of incidence D to this point C, then this joining line CD will be normal to the point of incidence. So you can say that this CDN shown in this figure is actually a normal drawn at the point of incidence D. And you can see I have shown the z-axis here by this dotted line. Actually this dotted line is just parallel to the z-axis, so you can also say that this is z-axis. And you can see in the figure that the angle between this z-axis and the incident ray in the first medium is actually equal to alpha 1. That is, the angle made by the incident ray with the z-axis is alpha 1. And so this theta will be also equal to alpha 1, you can say, because these two lines are parallel and AD is intersecting them. So this theta, which we have assumed earlier, that is simply equal to alpha 1. Now since the refractive index of the medium changes, so the direction of refracted ray will be different from the incident ray. And so let us consider that this dB is your refracted ray, and this refracted ray makes an angle alpha 2 to the z axis. It is clear? Now let us see. The angle between the normal CDN and the z axis is equal to phi 1, as you can see. And similarly, in second medium, again the angle between the normal and the z axis will be phi 1, because you know from geometry that this angle in the two media will be actually equal, because these are just vertically opposite angles. And you can see I have considered that this dp dashed, when you draw a perpendicular from D to the axis Z, then this perpendicular falls at P dashed, and I have assumed that this dP dashed is equal to X. But since we are considering that this point D is almost at P, that is AD is a paraxial ray, so in that condition this point P dashed will be almost at P. It means this PP dashed is almost equal to 0. Now you know, whenever the problem of refraction is discussed, definitely our basic equation is Snail's law. So we will start with the Snail's law to get the refraction matrix. And you know, here this angle I, which is angle between the incident ray and the normal, is incidence angle, and the angle between the refracted ray dB and the normal, which I have marked here by R, this is angle of refraction. And according to Snail's law, N1 sin I is equal to N2 sin R. I have written here, you can see, in accordance with the Snail's law, you can write N1 sin I equal to N2 sin R. In fact, when you will consider that the incident ray is actually a paraxial ray, then all the angles shown in this figure will be very small. So this I and R will be also very small, and you know, when I and R are very small, then sin I is equal to simply I, and sin R is equal to R. So this Snail's law, which is N1 sin I equal to N2 sin R, now can be written as N1 I equal to N2 R, because sin I is equal to I and sin R is equal to R. Why? Can you say? Because you know, in case of paraxial ray, I and R both will be very small, and in case of a smaller angle, sin theta is equal to theta, tan theta is also equal to theta, but cos theta is equal to 1. So on that basis, you can say Snail's law is expressed as N1I equal to N2R. But now see the geometry of figure. This I is simply equal to phi 1 plus alpha 1, and R, you can see, this is equal to alpha 2 plus phi 1. So in this equation you can replace I and R by this. So you can see I is equal to phi 1 plus alpha 1 and R is phi 1 plus alpha 2. So after this substitution, what will be your equation 1? You can see. So from equation 1, what you will get? N1 I, but I is phi 1 plus alpha 1, and that is equal to N2R, but you can see R is equal to phi 1 plus alpha 2, phi 1 plus alpha 2. Now let us simplify this equation to some extent. See here, you can write it N1 phi 1 plus N1 alpha 1, and that is equal to N2 phi 1 plus N2 alpha 2, N2 alpha 2. And so if you want to find the value of this N2 alpha 2, you will bring this term N2 phi 1 in another side. So you can see what will be the result. N2 alpha 2 will be equal to what? N1 alpha 1 plus N1 phi 1 minus N2 phi 1. N2 phi 1. And this may be written as N1 alpha 1, and if we will take in this last terms minus phi 1 as a common factor, then what will be our result? Take minus as a common factor, so this will be N2 minus N1 times phi 1. N2 minus N1 times phi 1. This is N2 alpha 2. And say this is equation 2. Now from the geometry of figure, we will find the value of this phi 1. See the figure. See here. This is your angle phi 1 and PC is equal to R. And as I have told you that this point P dashed is almost at P. So you can also say that P dashed C is equal to almost R. So if you want to calculate phi 1, let us find tan phi 1. See the geometry of figure. This will be simply X divided by R. Why R? Because this P dash C will be also almost equal to R. But as angle phi 1 is very small, so tan phi 1 will be simply equal to phi 1, and this phi 1 will be equal to X by R. So you can see this phi 1 can be written as X divided by R. So you can see as phi 1 is equal to X over R. So equation 2 can be written as N2 alpha 2 is equal to N1 alpha 1 minus, see the equation, N2 minus N1 times phi 1. But you can see phi 1 is equal to X over R. So we can write here X over R. X over R. Now, in the previous lecture, you have seen that this n times alpha is equal to lambda. And what is this lambda? Actually, this lambda is known as optical direction cosine. You know, this is optical direction cosine. You have already seen this expression in the previous lecture, so I am not going to explain it because I have explained this optical direction cosine in detail in the previous lecture. So you can recognize this term n, and product of n and alpha is written as lambda, and that is called optical direction cosine. So this n2 alpha 2, this will be written as lambda 2. N1 alpha 1 will be written as lambda 1. So you can say this is lambda 2 equal to lambda 1 and minus N2 minus N1 times X over R. Now let us introduce a quantity which is actually known as power of a refracting surface. In fact, power of a refracting surface. We have also seen this term during the study of thick lens, so I hope you have an idea of it. Power of a refracting surface. This is denoted by the symbol P, and this P is defined as N2 minus N1 over R. So you can use this result in this equation 3. So after using this result, you can see lambda 2 is equal to lambda 1 minus px and say this is equation 4. Now see the figure, see here. In fact, the incident ray is incident on the refracting surface at point D, and the refracted ray also originates from this point D. So if this x is written x1 for the incident ray corresponding to the point of incident D, and x is written equal to x2 for the refracting ray corresponding to this point D, then you can easily see that x1 and x2 are not different, but that will be same, because the height of the ray before and after refraction at D is same. So you can say here as the height of the ray before and after refraction, are same. So we can write x2 is equal to x1 and that equal to x. So you can see that one of the equations we may write x2 equal to x1 and say this is equation 5. And this equation 4 may also be written as equation 4. You can write lambda 2 equal to lambda 1 minus px, but x is equal to x1. So for convenience, now I am writing x1 at the place of x. And in this equation 5, there is no term containing this lambda 1, so you may write plus 0 times lambda 1. You may write it. Now see, these two equations 5 and 6 may be written in terms of a single matrix equation. So in matrix form, equation 5 and 6 may be written as. How you can write these two equations? You can see you have learned these things also in the previous lecture. So we will write in LHS a column matrix L lambda 2x2. And see here, we will form a matrix which will be actually 2 by 2 matrix with the elements which will be equal to the coefficients of x1 and lambda 1 in the terms of equation RHS terms of the equation 5 and 6. So you can see this will be 1 minus p. Here 1 is actually the coefficient of lambda 1 and minus p is the coefficient of x1 in equation 6. And corresponding to equation 5, you can see the coefficient of lambda 1 is 0 and that of x1 is 1. So this is just a 2 by 2 matrix, and this will be operated on lambda 1 x1. You can see this equation. You know the matrix multiplication. So when you will find this lambda 2, you can check. This will be 1 into lambda 2. Lambda 2 will be equal to, you can check it here. If you want to find lambda 2, what will be that? 1 into lambda 1. 1 into lambda 1. And minus p into x1 will be added. So this will be minus p x1. And you can see this is your equation 6. And when you will find x2, what will be that? See, x2 will be 0 into lambda 1. 0 into lambda 1 plus 1 into x1. You can check it. And this is your equation number 5. So I have told you that these two equations 5 and 6 may be written in terms of matrix by a single equation, and that single equation I have written in this equation A. So you can see what is the effect of this refraction or process of refraction. You can see actually the effect of this process of refraction can be represented by this 2 by 2 matrix. Actually here in this column matrix lambda 1 x1 in RHS represents the incident ray, and this column matrix lambda 2 x2 in LHS represents the refracted ray. So you can see when this 2 by 2 matrix is operated on this incident ray, the resulting ray is actually a refracted ray, and that's why this 2 by 2 matrix is known as refraction matrix. This is known as refraction matrix. So you can say, so the effect or process of refraction is given by the 2 by 2 matrix. 2 by 2 matrix. And what is that 2 by 2 matrix? You can recognize it here. We will denote this matrix by the symbol capital R, and that capital R, you can see this will be actually equal to what? This is 1 minus P, 1 minus P, 0, 1, 0, 1. And this matrix is actually known as a refraction matrix. This is your refraction matrix. A refraction matrix. And what is its effect on the incident ray? You can see, because I have told you that this lambda 1 x1 column matrix, this represents incident ray. And the column matrix lambda 2 x2, this represents a refracted ray. So you can see this refraction matrix just acts like an operator, and so when this mathematical operator is operated on the incident ray, the resulting function is actually your refracted ray. And that's why this matrix is known as refraction matrix. Now, see one of the important property of this refraction matrix. What will be its determinant? So you can see determinant R. or equivalently you may write the symbol for determinant. So what will be this determinant R? You can see this will be determinant of 1 minus P 0 1. And what will be this? You can see this will be 1 into 1, that is 1, a minus 0 into minus P, that is 0, and that equal to 1. So determinant of this refraction matrix is also equal to 1, and you have seen actually the determinant of translation matrix was also equal to 1. So you can say that determinant of T, actually this T is translation matrix, and determinant of R, both are same, and that is equal to 1. So this is the idea of refraction matrix, and you should remember this matrix, that is R equal to a 2 by 2 matrix, and that is the elements are 1 minus P and 0 1. And in the forthcoming lecture, now we will see the another matrices, that is reflection matrix and system matrix.